do your magic.
Thank you, Jousef. I'll try. I don't know if it's magic anymore. It used to be. Now I'm older, but I'll try my best. Yeah, I'll take a little bit of time, maybe 20, 30 minutes, and walk through a few different things. First, I'll introduce myself, actually. So I'm VP of Product here at SimScale. I'm a mechanical engineer. My master's is in thermodynamics, fluid mechanics. So this is like the world that I am somehow stuck in, but happily stuck in now, which is great. And today we're going to cover a few things. So I'll talk a little bit about who we are, what we do, just 2 slides. And then we'll jump straight into the topic where we're going to look at a battery pack analysis and how you cool it. So there's a battery pack on the right with a cooling plate above and below. We'll look at the full analysis, then we'll take a small section and look at how we can improve it. Then we'll look at how we could do that via API, so running potentially hundreds or thousands of simulations, like a whole design space exploration or optimization. And then we'll hopefully have a hands-on session if you'd like to join. You're welcome to. Jousef, did you, by the way, send a link to the project if everyone did want to try?
Not yet, to be honest, only that they should create an account.
Okay, we can do that on the way, I guess, as we go.
Sure.
Cool. So yeah, we're at SimScale. We're based in Germany. I live in Germany for some crazy reason. Still trying to learn German 7 years later, but I'm sort of getting close. The company had its 10th birthday last week. We have now 136 employees across the world, hundreds of thousands of users, like tens of thousands signing up every week, and yeah, millions of simulations in production now. Everything is in the cloud, so we don't have to host any of that ourselves. All of the data just can sit there and be safe. And we are a cloud native simulation platform. So there's a glimpse of what we have on the right-hand side here, and I'll take you through some of the important aspects. So we're cloud native. Everything runs in the browser. Nothing runs locally at all. So once your CAD is in the browser, everything gets pushed remote, and yeah, all of the workload, all of the simulations are done remote, post-processing, everything exists in one place. We can cover lots of different types of physics with lots of different solvers. So they're mainly split into flow and structural, but then there's tons of different solvers within all of those and loads of different capabilities. The idea being that any user can learn how to use the tool once and then apply it across lots of different disciplines. Being in the cloud, we have real-time collaboration, real-time support. So you can get live support within something like 1 to 2 minutes. You can be talking to one of our engineers, some of our experts. If they need to help you, they can jump straight into your project if you give them access, so you can get help when you need it. Again, because we're in the cloud, we can run at any scale. We'll talk a bit about that today, but you can run hundreds or thousands of simulations at the same time if you wanted to, and do massive kind of explorations of designs to really find the optimum. And it's cost effective. It's a SaaS platform, so you're really paying for what you use. So you get billed when you run simulations, but nothing too crazy. And the idea is that everyone can have access. So we want every engineer, everyone within engineering companies to be able to leverage the power of simulation. And then we have an API, which we'll talk about at the end of the session today. So we have the SimScale cloud platform that can go from 1 simulation up to tens or hundreds of thousands. And on the left-hand side, where we're not running too many simulations, we might be doing design validation. So we're taking probably a design that's quite mature, just validating it, making sure that it is okay, it's going to be safe, and it passes any certification it needs to. We might do iterative design. So we've run one design, figure that there's something we could do better, and we change it and improve it. All of those two are kind of done through the GUI, the graphical interface, but we also have the API, so you could start to do things more on scale. We have a lot of customers who set up things like, I guess, their templates or their own kind of apps. So their users in their companies never even touch SimScale. They just work with an application, really, really simple. It connects it to the CAD. It just pushes to SimScale, pulls the results back, and that's all they ever see. And then you could do many more things on scale. So we're going to look at design optimization today, where we're doing more of a design space exploration. But it goes all the way up to doing digital twins, where you could even connect to external data, push it to SimScale, and backwards and forwards. Just check there's no questions.
Just a quick question on the previous slide.
Yeah.
You know, some of these words are used by. So I'm not a buyer of this. So the question around the competitive landscape is just purely from an intellectual perspective. You know, what's the aha moment for when you talk about this and say AutoCAD or, you know, Dassault or maybe some of these bigger players that have been in this space for quite a while?
I'm also, by the way, not here to sell today, if it helps, if it's any consequence.
No, I just wanted to make sure that you didn't think I'm like kind of comparing you to others. It's an annoying question sometimes, right? Because it's like, well, but just curious, you know, because I've heard of Dassault quite a bit. We've seen some of their work, and there's a lot of simulation offers out there that claim to do digital twins and you know, exploration of the design. So is it the cloud native experience, or is it just the simplicity of the tooling? Just out of curiosity, what should I take away from?
It's a little of both. So I mean, I guess the simplicity is one of the aspects. We'll look at it today, and you can get your hands on it and test it if you want to as well. I mean, we are essentially product led, so almost everyone that ends up working with and subscribing with SimScale uses it without talking to us first. So the simplicity must be there. So that's one aspect. But yeah, the other one is scale and the kind of connectability of everything. So you don't have to just do one thing. So you're kind of freeing your desktop up. You can carry on doing whatever you want, and you can run 100 simulations on the side, all in parallel. So the scale can be really insane.
And I don't need MATLAB in my interaction with SimScale, right?
No, you could if you wanted to, but you don't need to. No. Okay. Most of our users honestly don't. Most of our users are, well, there's a little bit of a split between engineers and designers who are using CAD day to day. They might be pushing stuff to SimScale, but then I guess above or kind of adjacent to them is the methods team who are only doing simulations. They normally can't figure out how to change the CAD, or they're not allowed to touch it. But they're also doing simulations, and the collaboration between the two can work really nicely because everything again is in the cloud. And that's another kind of difference that we have that competitors, or at least most that I can think of, can't get close to.
Great, thank you.
No worries. So today, in a second, actually, I'll jump into SimScale and we'll look at this battery pack. So to kind of explain how it's set up. By the way, please jump in with questions at any time if you have them as we go, no problem. This is a battery pack, tons of different cells sitting inside it. It's obviously kind of a little bit reduced in complexity just to, for the demo purposes, but you get the idea hopefully. So there's tons of 2-watt cells. There's a cold plate above and a cold plate below. This is what the plate looks like, and you've got the inlet and outlet here. So you're pushing cold water in, could be coolant as well, and it's coming out at a different temperature. And what we want to understand is how well the cells are cooled. Are there any hotspots anywhere? Is there stuff that we could learn here that we couldn't learn on a test bench? I mean, that's going to be pretty obvious because it's hard to see inside a cold plate on a test bench, but we will anyway. And then can we improve the design? At that point, I'll jump across into SimScale. So this is what it looks like. This is us running in the browser. So everything I'll show you is live. There's nothing canned at all. So fingers crossed, everything's working well. Should be fine. But we can answer the first question. So what I'm going to do is look at the post-processor a little bit first, look at some results, and then we'll go through the setup to see how we got here. Again, ask questions if you have anything, totally fine. So we're showing here temperature on all of the volumes. You can see the scale at the bottom. So it doesn't get too hot, it goes from like 20 to 26C. And we can see over here, maybe I cut it in half, you can see that we got 26 degrees on the inside. So we know where it's hottest. And actually on all of the cells on the inside, there's kind of a strange pattern that oddly the ones on the outside are cooler than the ones on the middle. We weren't looking at radiation here. That maybe changed these things a little bit. But there's something a bit weird with the cold plate, right? That we're cooling the ones in the middle well and the ones on the outside not so well. And you would be able to see that on a test bench, but you wouldn't know why. So what we could do is put a cut plane higher up. So this cuts through one of the cooling plates to start to give us an idea of what happens as the water flows through. And you can see inside the water comes in over here and flows through two different directions, all the way to the outside. We have what...
Did you add that to the design, or is this just a different view of what's happening?
This is just a different view. So on the side here, I've got a few things set up. You can also just add them, but I've got a cut plane kind of higher up, just cutting through one of the...
Oh, you're cutting through, okay.
Mm-hmm. Yeah, I think I'm going to select it right, so you can see there's a weird like pink outline around the outside. Yeah, and the idea, I guess, or the thing that seems kind of weird is that these essentially meant to be turbulators aren't really doing much. They're slowing the flow here and there. On the right hand side over here, they're actually just directing the flow to the side, so it's not passing through the middle. But it's not really kind of making the flow super turbulent. And the flow is imbalanced. Maybe I'll change the scale a tiny bit to highlight that. But a lot of the flow is going through the center part, and it's not going through the outside parts. So like this is pretty red, right? Where the velocity is highest, is 0.2 meters a second. On the outside, it's less. So there's less flow going around the outside. And on the cutting plane, we can see as well temperature. To get an idea of, okay, what does that mean then? So there's less flow on the outside, but a big deal. Actually, we're extracting less heat as well from the outside. So we want to do something different here. The design isn't great, right? We need less flow on through the center and more through the outside section. We also would like to mix the flow a little bit better if we could. Obviously, the more it mixes, the more turbulent it is. Normally, the better heat transfer that you can achieve. And
is the color's temperature or velocity of the fluid?
Apologies, I just changed it now. So right now it's...
Oh, it's okay right there at the bottom. Okay.
Yeah, and we can change it to velocity, and then you'd have two scales. So all of the solid parts now are shaded by temperature, and on the cut plane that we have, we're looking at velocity. Does that make sense?
Yeah.
Okay. We also have some dead areas, like in the corners, where I mean, really we want a better shape here, maybe no cells even under here because the flow isn't really moving past them very well, or just a different, more linear kind of design or something, right, to avoid this kind of areas where the flow isn't moving. If you're interested, I'll do this and tell me if you're not. We'll walk a little bit through how to set the model up to get to this point. It's definitely not so complicated, but you start with your CAD. This is what it looks like, the same as the picture that we looked at before. You have two fluid volumes, one above, one below. You can create these inside SimScale. You normally don't create fluid inside CAD, right? You've got your solid parts, but you can create them inside SimScale if you want to. And then you need to set up your materials. So we've got aluminium, we've got the cell holders and the cells. All of this you can either use SimScale materials, you can create your own materials that stay saved in your library. So it's pretty kind of straightforward stuff. And then you tell SimScale what you know about the environment that you're putting it within. I'll then keep replying to the chat as well as we go. Here we've got a velocity inlet. So we tell it the speed that the water's coming in at and the temperature. And we have an outlet as well, which is just a pressure outlet. So you've now started to move the flow. The only other thing to do is to tell the cells, hey, you've got a heat load. And all of these, you can select them in bulk with the tool up here. The box selects, they all have 2 watts applied to them. And that's all you need to do. From that point on, you come down to simulation runs, press start, and kick off a new simulation. I've been messing around with this, so there's going to be some questions asked of me, but we could just run it anyway. And it'll tell you how long it's going to take, how much it's going to cost, and then you can kick it off and run it in the cloud.
But which cloud is this sitting on? Is that public knowledge? Or?
Yeah, it's public knowledge. Everything runs on AWS.
AWS, yeah.
Mm-hmm. Seems to be the main kind of standard. It's also good for us because we use I can't even think now, ARM, which they seem to have the only offering of. It's much faster than like the kind of standard stuff we were using before, the standard CPUs. But we use their GPUs as well for some of the solvers, which is pretty cool.
So it's late in the afternoon here in the US, so I'm allowed to show off at least once. So I learned, I'm not a simulation guy, that there are meshless, and lattice-based approaches to simulation. Mm-hmm. What out of curiosity, what is this using?
We have a mix, so we don't have anything strictly meshless. This is finite volume, so it's essentially a mesh, right? It's lots of tetrahedrons or hexagons. We can look at that as well, so you can see them on this cut plane here if I show them. We have lattice Boltzmann as well, which is essentially kind of a grid. That's used for fluid a lot. We have immersed boundary as well, which is kind of a blend of the two almost, so that it's not body fitted like this. So the mesh really here will curve around all of the parts. I can even show it on the cells, I think, so you can kind of see what happens. The IBM approach, I can maybe show you a model afterwards, kind of like cuts everything. And then it does math if you're in the US, in the background to figure out what's really happening in the gaps between the steps.
Got it.
So loads of different offerings, but we don't have anything.
You can pick your poison.
Sorry?
You can pick your options, sorry.
Yeah. But we also tried to guide our users a little bit, so you don't, it's based on some choices that you make earlier on, essentially.
You know, given I'm out of this space, and why has simulation become so popular and even though it was done in different ways over the last decades or so, right? We were, in the automotive sector, my understanding is they've always done these computational simulations. Is it sort of the same word, that democratization and compute power that we see in the AI? Is it about?
Yeah, I think so. I think companies have to do it as well. Now some are. You can't be competitive without. You can't iterate. I mean, if you can run, we just did a study with KSV, a pump company, and we did 900 simulations for them to do like a whole design space exploration. When I first started doing simulation, I was talking to guys in Halifax in the UK, and they were building a pump, and they were just test benching it and seeing what they got, then like filing bits away and testing it again. You can't iterate. It's just so incremental. And if your competitors are doing it, I think you have to do it now. There's no other way.
Oh, so it's still not the norm. Simulation is still not the norm?
No, I think it is now. It is now. The guys in Halifax, that was, I don't know, 15 years ago maybe. Then it wasn't always the norm, I don't think. But it's hard to find companies now that don't simulate. I think so anyway.
Thank
you. Yeah, there are. I mean, there's a lot of startups, especially in IoT electronics, who are not simulating at the beginning. So we're sometimes the first tool that they implement. But otherwise, most people are simulating. It's crazy. Okay. Okay, so we answered, I think, our questions. We figured out the maximum cell temperature. We figured out that there's some weird flow balance. There's some ineffective turbulators, so cylinders aren't working so great. There's some dead zones. And we could improve the design if we wanted to. What I thought would make sense then to start to improve the design, and I'll jump back to SimScale, is to not simulate the whole thing over and over, but simulate a subset of it. So here we've just got the cold plate, and this is the simulation that you can copy if you want to. I've actually just been messing around with it, so I'm not sure how great that'll be, but it should be okay. So this is just the cold plate, and now we can start to make changes. And instead of the other simulation took a couple of hours to run, this takes something like 15, 20 minutes, which means if you're going to do it step by step, iteratively, you can do it much quicker. So you can get insights much faster. The results look broadly similar, as they should, but we can see, yeah, the flow still comes through. Turbulators aren't doing too much, right, apart from stopping the flow moving through the center and letting the cells beneath get warmer. But otherwise, everything is very, very similar. But the nice thing now is that we can start to make design changes, and you can do that two ways. You can always push from CAD. So whatever CAD you might be using, you can make a change, push it back to SimScale, and then simulate again without having to set everything up twice. Well, you can do it in SimScale too. We have CAD editing here. It's not a CAD tool. It's definitely more limited than CAD, but you can definitely make changes. So there might be different things we want to do here, like moving some of the holes, deleting holes, moving edges. I thought one of the simplest things to do is just change the thickness. If you're allowed to, right, and if you can within the design space that you have, at least then we can get more water through it, which means hopefully better cooling. And then once you're back inside the simulation interface, all you need to do actually is duplicate your simulation, go to geometry and swap it for the new one. And then just simulate again. So there's nothing else to do other than run it. And then it's simulating in the cloud. You can carry on obviously doing other stuff. This is another advantage that we have, I think, of being in the cloud, that it doesn't matter what you're doing. You can be doing 100 different things in the cloud. You can still focus on a model and still post-process and still ask the questions that you want to. So nothing gets slowed down. And then, yeah, once you've run one simulation, you could compare it to another one. So you set up a view that you're interested in. I literally just ran this now, so I've got no idea how it's going to look. But you can compare your initial simulation to the thicker design. So one thicker design is still running, but the other one is complete. And yeah, so the same cut plane in the same place. Obviously, we've got the same flow rate, so the flow is going to be a bit lower. But what we could do is look at temperature and see if there's any differences between the two.
So I guess this is running, right, on the right-hand side?
No, I think that one was complete, but it had just finished now. I didn't think about it too much though, so I left the flow rate the same, so the overall velocity is going to be pretty low compared to the other one, right? Because the area is much larger.
So again, from a layman, the design teams, are they one and the same from the simulation teams in a typical company? The reason I ask that is, if you're doing sort of a design for X, like for cost, or a design for, for quality or whatever it is, and you increase the width of the plate, and suddenly that's 2 times the cost of manufacturing. So what do you typically see in terms of the relationship between the simulation team and these generative designs, violating the original spec or something?
Yeah, I mean, normally they're pretty connected. So either the designer, who understands all of the constraints, is doing the simulation. They're normally not going to make something thicker. They're going to do something internally to start to optimize the design. Or the simulation team might be doing the simulation, but normally what happens is they give that information back to the designer, then they decide what to do next, then give it back to the simulation team. So the process overall, they might get better results because the simulation teams generally know exactly what they're doing. I mean, shouldn't be the case with SimScale, but can be. But the iterative process takes much longer, right? If you're going from designer to simulator and back. So the idea for us is I can't remember the numbers, it's something like 70–80% of designers still aren't using simulation. And that seems crazy because we want them to, and we want them to be able to decide, now, okay, I know how to make this better or not. Then I can send it to the simulation team and they can validate it one final time.
But is that a future sort of role change for designers to get more into the real-time simulation of their designs? And
yeah, I think so. I think so.
Away. Kind of like a DevOps, like shift left kind of thing.
Yeah, but it doesn't take away from the simulation or methods teams though. So they I think they're always going to exist. I mean, they really understand how these things work and exactly what's going on behind the scenes, and sometimes you need to. And our vision, at least for them, is what you can do if you're an expert is set up a template for a designer, so they don't have to understand what's happening, but they can, without making mistakes, get quick insights. So I think both teams are always going to be, or at least for the foreseeable future, until we get towards AI, and they'll be needed.
Super cool.
Okay. Yeah, I'll skip this, I think, and just go straight to the design suite. So what we could then do, we haven't done this here actually, but what we often do is partner with lots of different optimization companies who want our information. So they will maybe run hundreds or thousands of simulations to get a whole design space, sometimes less. And then they can plot them all on a massive graph and interpolate between all of them and decide, okay, if you want to optimize for the lowest temperature and the lowest cost, it's this one. If you're looking at mass and something else, it's this one. And you can figure out what design is the best without ever having to build anything. We did it kind of simply. We could have kept this going actually, but we didn't. So we said, okay, you can change a few things, right? You can change the flow channel ducting sizes. We can change these turbulators. I think we should have actually changed the shape and not kept them as circles, but still, we could change the distribution, add more or less, and change their diameter. So we only ran something like 12 studies, these ones, but we could have run as many as you wanted. Once it's up and running, you can just keep going. And then you can plot them all. So you end up with something like this on the right. Normally you have hundreds of these dots with all of the lines between, like the pump that we looked at the top before. And yeah, you can say, okay, I want to optimize for pressure, like which one should I pick, or temperature, or like I said before, cost or weight, or whatever the main kind of design criteria is. You can figure out what design you need to choose. Cool. Any questions? What we could do, if you'd like to, it's up to you, is try this together. So I can anyway see someone in a project. If you want to, you can take a copy, make some changes and simulate it and see what results that you get. Otherwise, Jousef, that is probably a really super quick introduction to SimScale and simulation in the cloud.
So just one question on this community edition. So I went inside and just curious if to import this particular model you have for this battery cell, is that I have a tutorial here called stress analysis of a connecting rod. Is that the other options for me to import, you said, this particular model into my workspace?
Yeah, I mean, generally you can, if you you need to somehow get the CAD. So here you could actually download it and then upload it. The other way to do it is to simply copy the project that I have. So you can, if you use the URL that we have in chat, you can hit the copy project at the top. That will just copy the whole thing with CAD and everything over into your account, and then you can work on it from there. without doing any kind of file sharing, it's normally easier to just use the copy that you see here.
Okay, so I think I'm doing it. Let's see if that works.
Cool.
I don't have to upgrade the plan or anything, right? Okay.
No. The free version has 10 simulations of any type, or nearly any type. Yeah, you can just run them for free. After that, you can carry on running simulations, but you don't have any more numerical results. So you can still get pictures like this, and you can use them for, you know, for years if you wanted to, but you don't get numbers at the bottom anymore.
Got it.
Cool.
Yeah.
So yeah, I mean, you could make some changes. You could change if you click on the CAD, the geometry on the top left, you could edit it in CAD mode. Make some changes like the move that we did, or you could, yeah, anything else that you can think of here. So you could delete some of the holes or move some of the faces around, and then export it back, and yeah, then do a CAD swap, which is clicking on the geometry in the tree and choosing a different one. Then there's not really anything to do other than to press plus next to simulate and kick off a new simulation. But you could still make more changes if you wanted to. So the velocity, pressure, and the thermal load, any of that you could change if you wanted to as well. And hopefully you get some good results.
This is super easy to, I mean, the details are for the experts, but it's super straightforward to kind of copy the project and run a simulation. Wow. So the first tool I've used that, you know, can actually get me very familiar with these concepts. Thank you for this. I really appreciate it.
All good. All good. That's nice to hear, honestly. Yeah, we talked to a lot of users, so you have a very broad spectrum of experiences. But yeah,
I'm a software engineer. I don't engineer software anymore, but I'm sort of on the product management side, things like that. But yeah, you know, I joined this to get exposure to these concepts, and I was wondering if we'll have a tools like this just to explore. And so thanks. This is great.
All good. All good. I think there's other tools that are also really valuable and easy to use. Often they're embedded in CAD, but they're also normally quite physics limited. So we're trying to go the other way, where we're trying to be very broad with physics. Yeah, but still linking to all of the different CAD packages. So if you make changes in CAD, you can still connect back to SimScale and update everything and run the comparative studies.
Do you take this further in terms of like predictive maintenance use cases where you can create a model through data?
Yeah, we already do. We already are with Signify, which is like what Philips lighting is now called. So yeah, they're basically looking at predictive maintenance, and we're doing a project to run digital twins. And what they want to do is they want to understand if they have a whole road and they need to replace one lamp, is there another one that they should replace at the same time they close the street and turn off all the lights? Yeah, so they're doing digital twins to run like massive, I don't know, decade-long life cycles to figure out, okay, should we do this one as well? So yeah, there's a lot, I would say it's all possible. There's a lot that's possible. There's always more possible than I had in my mind when we built all of this. Does that answer your question, hopefully?
Yeah. I mean, you know, these are two words, predictive maintenance, but I was trying to see your numerical methods here are showing that there's stress in a certain part, or that the cooling is not going to work as successfully in here. And I was wondering if the community is looking to compare these models to what's really happening in the real world.
Yeah.
So I guess that's what's for me the theme of my question. But yeah, I'm sure they are.
Yeah, that happens. I wish we were at a different point, but humanity was at a different point and we were a bit more trusting but I guess there's too many companies that have just burnt this and it doesn't work so well. So almost always when we talk to companies and they're looking for simulation, we have to prove every time that SimScale works. But yeah, so almost always it's, hey, look, we got some test data, run the simulation, show us that it compares. It's just kind of standard these days.
Got it.
But the good thing is now we have the community plan, right? Users can do it for themselves. So they can decide for themselves whether they're going to get value, whether they're going to get accuracy, and whether they can use it. So no pressure on us. Cool. Anything else while I'm here? Okay. Then it's probably back to you, I would guess, Jousef.
I actually said in the chat, that's the point of the workshop where you should actually sell a license to all the people.
Yeah, I don't know. I mean, I've been in sales. I mean, I'm in product management, but everyone is in sales in a software company, right? That never goes away. But I also think that I'll talk about price as well, as seeing as you're asking, but I'd rather sell value. And then if someone finds value, like you can talk about licenses afterwards, right? But like figure out if it's going to be valuable to you first, and then the rest comes afterwards. And the cost kind of ranges. When we have like a 2,000 a user license for like a lot of the fundamentals. But we also have companies with hundreds of users and they have like massive team licenses, and it's a totally different scale at that point. But it starts from a couple of thousand a year, and that includes lots of simulations.